Hello students, this is Ahmed Mafi. Today we are going to discuss one of the crucial lessons, which is the internal forces. As engineers, we need to feel the stress in our structures. Yeah, deal with them as doctor deal with his patients. In order to write the proper prescription, he need to understand and feel the pain in his patients. We do the same thing for our structures even before they exist in order to have a robust design. As you see in this photo, one of my beloved bridges here in Edmonton, the Arch Bridge, the iconic Arch Bridge that we already have, we could find that the cables carry tension forces internally, while the Arch Bridge beam carry compression, and this horizontal beam here try to prevent this arch from opening, so it will carry tension forces. When loads are applied to a beam, internal forces develop within the beam as a response to these loads. We can visualize these forces by making an imaginary cut through the beam and examining the internal forces acting on the cross-section. Basically, we have three types of internal forces. The first one is what we call normal axial force. So normal axial force come from like loads applied parallel to beam axis, which actually will create internal forces perpendicular to the beam section as we see here, and they have a uniform distribution, so we could represent them by their resultant, which what we call normal axial force. Same thing for the second type, which is the shear forces. They come from external loads that apply perpendicular to the beam axis, which will create internal forces parallel to the beam section as we see, and we will represent them with the resultant V. The third type is what we call bending moment. To understand bending moment, let's use this paper fan that we used to make during our childhood. I think this is our first design as engineers when we were at kindergarten. So let's imagine that this paper fan represents our beam. If the beam experiences tension, we could see that the fan sections move away from each other. If the beam experiences compression, its sections move closer to each other. However, if a downward force is applied perpendicular to the top section here, the fan, we could see that like we will have a bending. So we could see that the top part of the fan or the top fibers come together, which means that we have compression at the top, and while the bottom of the beam are coming or expanding away, move away to cause tension. So if we see this in our beam, we will see that like we have compression at the top, compression forces, normal forces at the top, and tension normal forces at the bottom. These forces cancel, we could like cancel each other if we would like to have a resultant for them. They will cancel each other and they will cause like what we called bending moment. So in conclusion, we have three main types of internal forces. Now, someone might ask, what is the importance of bending moment? Yeah, you told us it's crucial for taking informed decision. So let's have this example to see how we could take those informed decisions. You know, like one of the most famous materials in construction engineering is the reinforced concrete. It consists of plain concrete, which could handle compression carefully, but on the other hand, it cannot handle tension. It will fail under multiple cracks. That's why we need to use reinforcement steel in area where we expect to have tension to handle this issue. So if we have assembly supported beams that have a load at the middle and effect in the downward direction, where we should put this main reinforcement of this beam. Any volunteer? Yes, we should put it at the bottom. If you remember this fan example, the tension take place at the bottom. What if we have a cantilever beam? Just let's recall this fan example. You will find that if we have a fixation here and we apply a load here, we'll have tension at the top as you see. So this means that we have the main reinforcement at the top. So you see, just the sign of the bending moment, the direction of the bending moment could affect our decision or for design. What about the value itself? For sure, the value will help us to take an informed decision about the dimensions of the beam and their reinforcement as well. So that's why in your upcoming design courses, the first step that you are going to do is just to calculate the internal forces. That's why they are crucial for us. Therefore, engineering community has agreed to use consistent sign convention for our internal forces. For normal forces, tension is our positive sign convention. So if it's on the right section, it will act to the left. If it's on the right, in order to have tension, it will act on the right to the right. For the shear forces, like the clockwise rotation is the one that causes positive shear. So if you study the right portion, this means that if the shear is upward, it will be positive, and vice versa for the left. Because this is a bit confusing, just connect it to this example. Imagine that you are traveling to Vancouver in this multi-lane road, and the right lane is always upward, while the left lane is downward. So it's similar to shear. Upward if we study the right, and downward if we study the left. For the bending moment, it's a bit easier. The positive is a bending moment that causes tension at the bottom. So if we study the right portion, it will be in clockwise rotation, and vice versa for the left one. Now, let's take an example to see the calculation steps for internal forces. As we see here, we have this beam that could represent a girder beam in a bridge, and those loads coming from a car that crossing the bridge, and the driver decided to press on the braking to stop at the middle of the bridge, as we see. So we have this braking force, and we have the vertical load come from the car. And we need to calculate the forces or the internal forces as a section CC. The first step is to draw the free body diagram and calculate the reaction as we did previously in Eng 130. So we have hinged support here, we have two reactions, YA and XA at point A, and we have one reaction for the roller support, which is YB. By applying equilibrium equation, as we all know, we could just calculate those reactions. I give it here for your reference. We should know how to do this previously. So the second step is to calculate the internal forces at the cut. So now we know all the reaction. We need to study the internal forces at the cut, which is 2.5 meters away from the left support. So I'm going to study the left side of this beam because it's a bit easier. We need to assume the positive direction of the internal forces. So for the normal force, it will act in tension. For the bending moment, it will act in anti-clockwise direction because this will make the bending moment create tension at the bottom and compression at the top. And for the shear, just remember our trip to Vancouver. Now we study the left side, so the downward will be the positive direction. Now let's apply equilibrium equation for these forces to get the internal forces. So in x direction, if we apply this, we have N in the positive side and 2 kilonewton in the negative side equal to 0, which means that the normal force will equal to 2 kilonewton, and it's positive. This actually refers that we have a tension normal force. For the shear, we could apply the equilibrium in y direction, so we could find that the shear will equal to 5 kilonewton. And for the moment, we could apply moment at point C. So at point C, we know 5 kilonewton effect with a moment. So we need to multiply this 5 kilonewton by 2.5 meter. And this 5 kilonewton cause a rotation in clockwise direction. So we will get it a negative. Then we will add the moment itself, which affect anti-clockwise direction. So it will be positive moment. This will equal to 0. And by doing math, we could find that M will equal to 12.5 kilonewton meter, and it's positive, which means that the tension will take place at the bottom of the beam as we done previously. And here is the steps provided to you without my handwriting if you don't like it. So in conclusion, today we have learned together the types of internal forces importance, the sign convention rule, and the simple calculation steps using section methods. So in addition to method of section, we are going to learn how to create functions and also draw diagrams for internal forces next time. This actually will help you to visualize the internal forces. So in my opinion, like by the end of this course, you will have this paradigm shift that make you visualize them even while you are hanging out with your friends. So stay tuned and see you next time. Thank you.